So it's a great pleasure for us to have Nate Lewis talk to us today, because I remember that we're trying for at least 3 years now to get you to our meeting. Nate Lewis is a professor in the chemistry department at Caltech, and he's interested in artificial photosynthesis. And most importantly, he's the principal PI on the Joint Center for Artificial Photosynthesis, which is a joint project, among others, between Caltech and Lawrence Berkeley Lab. And there are a lot of connections between JCAP and the ALS, between a number of beamlines, and we're looking forward to your talk.
Scale to the decimeter scale with technology that doesn't yet exist in 5 years. And we're doing them all at once because you can't possibly get from here to there. If you spend 5 years developing components and then 5 more years figuring out how to put them together, and 5 more years figuring out that it doesn't work when bubbles ruin your day, and 5 more years figuring out that then you don't know how to make a lot of it, and 5 more years after that when you figured out you did it all at the wrong pH and the whole system corrodes, and over again. So JCAP involves all at once, highly translational, highly parallelized research. It's arguably a new paradigm for the way that academics do work. It's really a response to Secretary Chu, who told Congress that that's what he wanted the hubs to be. He wanted them to be a different way of doing business. And so you have to think about it differently. JCAP is what we like to say is the world's best funded startup company. We have $122 million in our A round over 5 years, and our job is to show that it was worth it. We are operating in response to the Secretary's desires for what these hubs should be under, quote, one roof, where we couldn't move the beam line, so we have an outpost at SSRL. We have users at the ALS. Other than that, everybody works in one of the 2 JCAP facilities, either at Caltech or at LBL. There will be a new building just right near the ALS soon for 2 years for JCAP, and now we're in temporary space down the hill. The other partners, like Santa Barbara, Irvine, and San Diego, Santa Barbara is important but not twice as important, that's a D, they send their people to one of these 2 buildings to work, or we don't do it. Because the whole philosophy is that the hub has to be a place that does projects that can only be done in a hub, or that dramatically benefit from being done in a hub. And our job isn't to just fund individual projects at individual research groups, because that's what DOE's job is. That's not what our hub job is. We're doing highly parallel R&D, and we want to think about the end goal. So what's the start? This is the start. The start is that we know that it is possible to make fuel from sunlight. Now, of course, we know that because plants did it. They get an A for inspiration and a D- for execution. Because if you take the fastest known growing plant and you take the amount of sunlight, the 100 milliwatts per centimeter squared that hits that at peak, multiply it by all the energy in a year, and divide that by the higher heating value or the delta G of all the biomass in the fastest growing plant, it's less than 1% total efficiency. So ask an engineering design class for an answer, get the best answer, 1%, D-, right? 99% wasted. You can take minerals like this, strontium titanate. We just saw a poster about one of them. They probably had no clue it actually did this. If you dunk it in water and shine light on it, that you get hydrogen and oxygen from water split, and the free energy stored in that hydrogen and oxygen compared to the incident sunlight that hits that is already twice as efficient as the fastest known growing plant. And this stuff doesn't have to regenerate and waste 30% of its energy just to stay alive. It just goes on and on and on. What's even more impressive is that, of course, the band gap of strontium titanate is 3.2 electron volts. So even though it's 1 or 2% of the sunlight efficient, it's wasting 90% of it because it doesn't even absorb it. So it should be possible to lower the band gap and make something that's red, green, or blue that gets much better efficiencies. It should be possible to do that, but right now there are 3 things you want, and only 2 of them you can have at any one time. You can have the system be robust, you can have it be efficient, you can have it be cheap. Pick 2. Systems that are robust and efficient aren't cheap. Robust and cheap isn't efficient. Efficient and cheap doesn't last. That's our job. 2 out of 3 is great in the baseball playoffs, but it's not good for us. We have to go for the trifecta. So we think biology did get right the inspiration. You want 2 photosystems, not 1, because then you can lower the absorption threshold down to something like 600 or 500 or even 700 nanometers, and therefore absorb a lot of the solar spectrum, instead of having the single photon threshold exceed the thermodynamic 1.23 volts you need to split water. So you string up 2 of them in D cell, like flashlight batteries. Each one of each only gives you half of the energy. Probably also got it right in that you need a membrane, because I forgot to say that this is a parlor trick. It's not a real system, because it co-evolves hydrogen and oxygen in the same place at the same time. And even though you can claim a scientific breakthrough, this is not a technology, because nobody will build such a system other than a solar-powered Hindenburg, right? So we have to find a way to separate those products and neutralize the inevitable pH gradient that will otherwise occur, which means develop some type of membrane-inspired system that does this artificially. In addition, this is probably good because the hydrogenases and nitrogenases that do the reduction of the fuel from CO2 and water are not oxidatively stable, but they never see an oxidizing environment. And the manganesite and the oxygen-evolving complex of photosynthesis, that is oxidation source of all oxygen in the atmosphere, is not reductively stable, but it never sees a reductive environment. So by compartmentalizing these things, you can partition out the problem of stability under both oxidizing and reducing conditions to 2 separate, hopefully tractable problems. That's the blueprint that photosystem 1 and 2 gives to us. So let's just build it ourselves out of pieces that are much more efficient than these organic chromophores that have to have electrons hop to organic molecules, that don't have the mobility that inorganic solids do, that don't have the light absorption and tunability that inorganic solids do, and that don't have the robust catalysis. After all, Rubisco is the most expressed enzyme in the world because it's probably one of the worst enzymes in the world, so nature has to make a whole lot of it in order to get the activity it needs. We can do better. This is the vision of JCAP, a slip and slide that you roll out on your roof or in your farm that's a membrane that wicks up reactants like water, CO2, and sunlight, vents the oxygen to the product, and then keeps down below either the gas hydrogen or the liquid that comes out from the fixation of CO2 by 2 such photosystems across, basically supported in a photoactive piece of plastic. So like nothing you've ever seen before outside of a plant. Okay? That's the goal. It's a noble goal because we know you can do this 10 times more efficiently already than the fastest growing plant. And when you start to think about trading food for fuel and about no potable water and no arable land needed, 40% of global transportation cannot be electrified, and there's no such thing as a plug-in hybrid airplane. We're going to get from there to here in a clean energy economy. We've got to figure out how to do something like this. The reason we want nanorods or microrods is because one of the key ideas is that they orthogonalize the direction of light absorption and charge carrier motion. And in doing so, you can then have a long axis to absorb the light and tolerate a high level of defects in the material because carrier concentration can be moved sideways. And that can give you the so-called radial advantage. And liquids make the perfect conformal radial contact to a whole bunch of these things. And you'd like one to have the high band gap and the other to have the low band gap to get your tandem structure. You don't want them both at 670 nanometers. You want one to absorb more of the blue, the other to absorb more of the red, while collectively producing the over 1.23 volts you need to carry out fuel formation. Unlike in a solar panel, we can't get 1.22 volts because we get nothing. We need 1.23 or more to get our fuel. Well, actually, this isn't pie in the sky. This actually, pieces of it work. Here's silicon microrods that if I had chosen to, I could have spent 45 minutes telling you about the results that we've gotten growing them. We grow them by catalyst pattern growth from vapor, liquid, solid, copper, nickel, or gold. We grow these beautiful single crystal micro rods. We peel them off of a wafer by going to Petco and getting polydimethylsiloxane or Nafion, not from Petco, but from the fuel cell industry. And then you put that into a membrane, you yank it off, the rods come off with them. They become either partially or fully embedded in these membranes. This is the best kind of organic solar cell. It's an organic solar cell when the organic material absorbs none of the light, and it's all absorbed in the inorganic chromophores that we can orient, that we can grow, that we can put catalysts on, that we can even laminate together, one on the bottom and one on the top, through a proton conductive and electrically conductive membrane to make something that does look like that. Just doesn't work like it needs to work yet, but this is not just PowerPoint. It really exists. When we decorate these things with platinum catalysts on this bottom half, we can convert at nearly record efficiency sunlight into hydrogen. So we can do that. And when we platinize these things, that works pretty well, but the platinum challenge is that it's not earth abundant enough to give us enough resource available to really do a globally scalable thing. So we'd like to replace that with earth abundant elements like nickel molybdenum, which we've shown on these high surface area supports actually have catalytic activity close to that of platinum. The challenges that I'm going to pose are going to come after the next slide. The next slide is that we can actually laminate these things together. And so we can take one of these layers below and one of the layers above and make this thing. This thing was made 4 years after that PowerPoint. This thing is a real thing you can hold in your hand that is the real world implementation of that vision, with only one minor problem: it doesn't work. The reason it doesn't work to do this is because if this is silicon and this is silicon, as we did to make this bologna sandwich with a Nafion membrane that conducts protons, is that two silicon samples don't give us enough voltage to split water. Right? So we need to have a top material, and besides, it's not a tandem structure. So what's JCAP's goal? Discover that stuff. Build the pieces to get us off the ground as the Wright Brothers, to show within 5 years that we can make something that works. We know that the first product is never the last product. The first iPhone is not the last iPhone. And so it would be foolish to think that we were going to be done in 5 years and be able to save the planet with this technology. What's smart to think is that we're going to show it can be done and then figure out how to make it faster, better, cheaper, and then keeping optionality open that we probably are going to reduce water to hydrogen first, is 55 molar, and then reduce CO2 by 6 electrons to methanol later. But we want to keep optionality open to do that at a later date. So JCAP is really organized around those gaps. Right? We've got a team of people working earth-abundant light absorbers and photocatalysts, because if you don't have those right catalysts to give you 1.23 volts, we get nothing. And they better be earth-abundant. We've got a team of people working on low overpotential catalysts. I don't care if they're homogeneous or heterogeneous, but the sun is not a laser. Photons come in one at a time, make and break electrons, makes 2 or more in the same spot at the same time. We need catalysts to do that. We have to have membranes to separate the products. The membranes the fuel cell industry uses, like Nafion, are too high performance and too expensive, and they don't work in alkaline media, where we want an option to be able to work, because some of our photochemical materials are only stable in alkaline media, like the metal oxides, that they leach their metal in acid media. We don't have a system unless all the pieces work under the same conditions. We just have a paper or two. That's not good enough. We have to be able to integrate them together. This is what I lovingly call the Mr. Potato Head team for those Toy Story fans, right? I give you a catalyst, I give you a membrane, I give you a light absorber, and you have to put them together and make smiley face out of Mr. Potato Head, not frowny face. It all has to work together, at least as well as they work separately, or we have nothing. We have an emergent phenomena team. The first thing you saw was that this works. It makes bubbles. But you know, bubbles can ruin our day if we make bubbles and they diffract light away from the light absorber, if they don't let us transport reactants and products through our structures, and if they clog up the flow in the real deal and we're really making a system, not just a little thing under a microscope. So we got a bubble team trying to work on the phenomena of bubbles and flows from the first day, because it's a place where we could get creamed if we don't deal with it. We've got to scale up because we build real devices, as I'll show you. Because we can't get $122 million and have this little thing under a microscope when we're done, right? Nobody's going to want to do that again. We've got to have something real you can hold in your hand that you can show your friends and neighbors, and I can show Congress and says, this is what you paid for. We built the world's first solar fuels generator, and here's the pieces that we put together. Right? And then it better be scalable and sustainable, because if what we build isn't something credible that could be scaled up to something where we could make a lot of energy, that is the E in Department of Energy, right? That we actually aren't credible. So we have to be able to tie them together and make something useful in the end. That's how we're organized. Those are our 8 projects. We've got technical staff. We've moved people from around the world to join the hub. People are dropping their careers because this is a unique opportunity to get together in order to, under this one roof, really try to see if we can take what's going on in disparate laboratories and unify it in this synergistic way. To give you a feeling, this was our all-hands meeting last year when we are at a 3rd strength in JCAP. Okay? And we're going to have twice as many, yet again, people added on to this in the next year. Right? So if you're interested, there are still plenty of opportunities in JCAP. It all starts at the prototyping, which is unusual for a scientific effort. But we have an end goal. The stuff has to work. We are building from the first day real prototypes with knowing that we only have dummy parts, parts like that strontium titanate that only work in the ultraviolet right now. But they'll let us debug how all the bubbles and flows and everything else works if we adjust the UV flux to match what we expect we'll get in the visible region of the spectrum. So we build prototypes knowing that they don't have the final parts, but knowing that they'll allow us to get something that works. We have our own, right down the hill, rapid 3D prototyping machine. We can take any SolidWorks object and convert it within 24 hours into a real thing that you can hold in your hand by this multi-layer inkjet printing, spewing out different levels of plastics and metals. So if you have a good idea on how to build the next prototype, you should let us know, because we will build it and test it and see whether it works or not. But before that, we will model it, because we run on NERSC 3D COMSOL multiphysics models of the IR drops, of the flows, and of all the things we can simulate in order to make sure that what we build will actually have acceptably low mass transport problems, resistive problems. We can solve Poisson's equations here, so we know what the IR drops will be for these geometries. For instance, we've shown that given the conductivity of normal electrolytes, even like 1 molar sulfuric acid, that you have a certain thickness and a certain height that can be tolerated, above which you get too much IR drop, in the same way that you would make a solar cell without grid lines. You don't make a very good solar cell because the IR drop in the tin oxide becomes too great. And the resistance to the electrolyte becomes too large. This has been ignored previously. We faced it the first day. The second day we faced is it's fine to say we're going to make a photovoltaic cell and put tin oxide on top of that and insulate it from the liquid. Except that the instant you put it in sulfuric acid, all that tin oxide just dissolves. All right? And so now we have corrosion problems and barrier problems that we face that you never face in PowerPoint, you face when you build the real deal. So we build them. They look like this. There are slats that have optimal angles for the angle of incidence, representative latitudes for the sun, and an Nafion membrane to separate the reactants from the products. And we build such designs. We then test them in water vapor, which sounded crazy. How can you do electrochemistry in water vapor? It works just fine, because as long as the Nafion stays hydrated, then the catalysts see liquid water, essentially. This is the reverse of how a fuel cell works, where in comes gaseous hydrogen and oxygen, out comes water vapor. So let's put in water vapor and photo drive the reverse to make out gaseous hydrogen and oxygen. This works fine, except that it does raise issues of what is the environment around our catalysts when we're trying to reduce CO2 in water vapor as opposed to in liquid water, and will they function, and are they transferable, how they're different. So it's an example of the kind of both opportunity and challenge you get when you try to build the real deal instead of kind of hiding in the sand in the lab. That's just not acceptable to us. Light absorbers. We got to have pieces to absorb light. Our first shot was silicon, of course, we still have in our back pocket. But silicon's not stable in alkaline media. And so if we want to build a system where we can use the earth-abundant catalysts that are already available, like nickel and nickel hydroxide from alkaline electrolysis, then it has to last in alkaline media because they're soluble in acid. And then we need an alkaline membrane, not Nafion, to pass as hydroxide, not protons. Neither an alkaline stable photocathode nor an alkaline membrane that's stable yet exists. So we've got challenges there. If we go to acid, we can use silicon, but we don't have the photoanode. We have the membrane, but we don't have the earth-abundant catalysts. So challenges there exist. Different challenges in each case. Right? We looked at tungsten selenide, P-type tungsten selenide. It's a layered compound, van der Waals system. Looks like graphite, except it's tungsten and selenium selenide rich on that top van der Waals plane face. We reasoned that this would work because the metal sulfides and metal selenides are good hydrodesulfurization catalysts. And since at high temperatures they make hydrogen and split hydrogen, it made sense that at low temperatures with electrons and protons, they might do the same thing. And indeed, this turns out to be a really great photocathode, comparable to silicon, but more importantly, it's stable in base. So now we open up another system in the toolkit to be able to study where these entire series of metal sulfides and selenides have never really been studied extensively before. The questions that arise then is it only that the van der Waals plane is the photoactive plane, and what is the nature of the edge sites and defects? Are they actually catalytic sites or recombination sites? We hope they're catalytic sites, because if they're recombination sites, then we have to find a way to make large areas of the stuff with hardly any edge grain boundaries involved. But if they're catalytic, then we want more of them. Or if we can find a way to get carriers out there and make them catalytic, we want more of them. This is a JCAP problem. It's to understand how to take a material and grow lots of it and understand where the active parts are and how to make more of them and suppress the stuff we don't want. Another JCAP problem is how do we very rapidly take out of the, as you'll see, millions of new light absorbers that we make every day and understand where the big fish are in the oceans, not just the little minnows. And we developed a rapid scanning measurement we call the wedge, where we take a different thickness of our light absorber and we just kind of bevel its thickness and we photo excite it, and as it gets thicker and thicker, more and more of the carriers are created in the bulk and less to the interface, and we can just raster that light beam or an X-ray beam and then measure the diffusion length. And stuff like this we don't want, stuff like that we do want, and we do this for lots of samples, only then investigating the new materials that look promising as opposed to the ones that don't. This doesn't mean you couldn't develop a lot of new chemistry to make a rotten material initially work well. It does mean that if you're going to do this in 5 years, we want to explore lots of stuff. Every hit is a PhD thesis. What about these catalysts? This is the so-called volcano curve for catalysis of the hydrogen evolution reaction, known for now 100 years. Platinum's the best. The reason the volcano curve exists is really easy to understand. You want the concentration of intermediates to be about 50% coverage, because if the bond is too strong, you've got all the intermediate, you can't desorb it. If the bond is too weak, you don't have enough intermediate. And so when it's just right between the papa bear and the baby bear, you have the activity, because the denominator is minimized when 50% and x and 1 minus x. So makes good sense. Platinum happens to have that. But there's not enough platinum to cover even a monolayer over an area needed to make enough energy from the sun to make a difference. And so we've got to find other materials. So one approach we have is make bimetallic alloys, where we try to exploit spillover effects when some material intimately bonded together that bonds too weakly with some bonded too strongly will be just right. Tungsten carbide is an example of a poor man's platinum that can be electronically used to support platinum and fool it into thinking it's on platinum when it's actually on tungsten carbide, W2C, for instance. Nickel molybdenum is another example of that, where we take two earth-abundant materials and alloy them together, and it's almost as active as platinum. So we're trying to explore this bimetallic phase and more combinations as opposed to the pure metals to try to come up with the earth-abundant activity that we need. We're doing this with advanced STM imaging, but we're also building our own end station at SSRL, where we're doing ambient pressure in situ X-ray photoelectron spectroscopy. At grazing incidence with differential pumping, you can actually get enough escape photoelectrons off of the near surface layer to be able to do that. Anders Nilsson is leading that charge, and because JCAP is paying for that end station, we're going to own it. We're going to release it to the community after it's designed in part, but we're going to have that near ambient pressure XPS capability to in situ characterize the chemical states of our materials on the hard X-ray source. And there's a similar system that's on the ALS that we're also using for this purpose. Well, we've already got some earth-abundant catalysts discovered for the nickel-iron borides are comparable to the best catalyst in alkaline media, iridium oxide. But we don't actually know what the oxidation state is and what the active area and active sites on these systems are. This was done here at JCAP North, as we call it, at LBL. And so then we went to use RICS, so we could help identify what the structure is of the active sites in these materials. And this is just an example of one of the types of things that we use the light sources to be able to probe deeply after we discover things. But we have a lot more discovery to do. In the molecular catalysis area, we're almost heretical in that although there's beautiful work done on modeling homogeneous catalysis of enzyme active sites, we're doing almost none of that in JCAP because we feel that it's beautiful to do the basic science, but 98% of the real-world catalysts are heterogeneous catalysis. And we know the best ways to make water into hydrogen are all heterogeneous catalysts. The only ways so far to make water into oxygen are all heterogeneous catalysis. So mostly in JCAP, we are doing heterogeneous catalyst development for those, with one exception, CO2. Because for CO2 reduction, we need product selectivity. Because we want the 6-electron reduction to methanol and not the 2-electron reduction to CO. And so we believe for CO2 reduction that ligand design and secondary sphere interactions will be critical. So we've developed some catalysts. Cliff Kubiak at UC San Diego is leading the charge there that actually show selectivity of binding and reducing CO2 relative to protons. This is pretty remarkable. And after all, if you're going to work in water and in the ambient air, you're going to be able thermodynamically to reduce protons when you're reducing CO2. So we have to find ways to do product selectivity, which we've been able to demonstrate, but we don't yet know what the key intermediates are. We don't yet know how to tune the system to make methanol the 6-electron product and not to make CO the 2-electron product. These are things that we're very interested in using the LCLS for, as well as the synchrotron light sources to understand the structure and composition of the intermediates that are involved in CO2 reduction on our molecular systems. We also have a benchmarking group. Again, unusual for an academic environment, but everybody that reports a catalyst always reports on their novel best catalyst, because otherwise you don't get it published. Well, everybody's catalyst can't be above average in the best catalyst, yet everybody tunes the conditions under which they test things to make sure that they have the best activity. That's great for doing science. It's not great for advancing technology. So we have the supposedly honest brokers benchmarking team, arm's length people of professionals whose job it is to run catalysts in the literature or new ones only under the standard set of conditions that JCAP cares about to build the device. We only care about building a device at pH 0 in Nafion or pH 14. There's no membranes at pH 7 that have ever been invented that can work. The reason is the transference number of protons, which after all are at the minimum at pH 7, doesn't support you neutralizing the pH gradient there. And until somebody puts a credible scheme at pH 7 how we build such a device that works, then we're not going to worry about it. So we benchmark things at pH 0 and pH 14 because those are the only places our modeling shows we can build something. We've developed this approach to measure the overpotential at 0 time and the overpotential after 2 hours arbitrary, and then you visualize the stability and the overpotential on these graphs. That if things are close to the origin on the 45-degree line, that's good because they have a little overpotential, and if they're right on the 45-degree line, that means they're lasting. All right? So we're bookmarking all of the catalysts that we can find in the literature, and people send us new ones because DOE has said if JCAP doesn't benchmark it, it doesn't count, which is perfect because we have to be the clearinghouse to be the honest broker for any new catalyst. And by the way, if it's really good, then we're going to get you beamline time really soon on it, so you'll figure out how it works. And we're going to put it in our device, because ultimately, if your catalysts don't make our device better, they don't count. We also have to do interfaces, because as I said, let's take platinum, great catalyst. Let's take silicon, great light absorber. What happens when you put platinum on silicon? You make platinum silicide. That poisons the platinum and it poisons the silicon. So you end up with nothing. So the interface team has to, from the beginning, keep the stuff working as it comes out of the stovepipes, or we don't have anything in the end. Right? There are two approaches to that. One is to link molecules to these light absorber surfaces, and we have to develop and are trying to develop a general linker chemistry where the linker won't degrade, because if the linker has double bonds and unsaturation and we're working under catalytic hydrogenation conditions, the linker will be gone. Or if the linker has abstractable CH bonds, then it's gone. We can have all the great linker chemistry in the world in scientific papers, but if we don't develop robust systems that work where the device will work, then we don't have anything. So JCAP is trying to do exactly that. In addition, we have to get catalysts on there like this one, and get the catalyst and the surface to function at least as well together as they did separately. And so we're trying to use the LCLS as well as soft X-rays to probe the catalytic activity of these model catalysts when they're linked through our linkers onto photoactive materials, and compare them to what happens in solution. For the real aficionados, we have a parallel effort that doesn't just involve linkers, but that involves just direct surface interactions of molecules protected from surfaces by thin ALD layers, of actually using quantum confinement and nanoscale to have the so-called tunneling effects, that when you get very small, you've got pinch-off of the electric field around a small metal dot that localizes the charge there and prevents recombination from occurring. And so we've got two interface groups, one solids on solids, the other molecules on solids, and they kind of work in friendly competition, which is fine by me. And then we have the mesoscale, because we have to have membranes to hold these pieces together. And on top of that, if we have one nanorod, that's not like a whole lawn full of nanorods with all of them pointing up toward the sun. We've got to find ways to orient them all, or we don't have anything, right? So we have efforts in both of those. This is one example of what we did in JCAP. We immediately said we would really love to not have to make that intervening layer in the membrane be both ionically conductive and electronically conductive. It has to be in that initial picture, because the top rods have to electronically be ohmic contacted to the bottom rods to get carriers to move between them. That's okay, but that's a tall order, and so if we move to self-align the top with the bottom in the so-called Q-tip structure, then the only rod that needs to penetrate is the same one at the beginning, and then we don't have to have the intermediate layer of bologna sandwich that conducts the electricity as well. So we designed this and built 5 of them, and then decided, since none of them worked, that an hour in the modeling effort would save us a week in the lab. And so Kate Fountaine, in fact, did that. And we found out the reason is that these corners are bad because they launch surface plasmons, even with things like ITO or aluminum or gold at very thin levels. And you need to avoid corners. And a lot of optical modeling and simulation showed that we need to round them off in the so-called Qtip design. We did that. This is tungsten oxide electrode deposited on silicon, and that actually works. And furthermore, the rod that penetrates the membrane is the silicon microrods. It pokes out the other side. Catalyst goes down below. We don't need light absorption below. They're self-aligning. This is really good and almost would work for us, except that the band gap of tungsten oxide is too big. It's 2.6 eV, and we need something that's more like 1.7 eV. So we're searching for that magic photoanode earth-abundant material still. In addition, when these photoactive rods penetrate the membrane's now disrupted. If it's Nafion and it conducts protons by having water channels from pool to pool, and you poke a rod through it, it's not obvious that it'll still conduct protons at all, because you disrupt the local order and structure of that Nafion as it self-organizes around this hydrophobic interface at the surface of those silicon microrods. So grazing angle, small angle X-ray scattering done at the ALS by Rachel Siegelman shows us the structure of Nafion when it's got rods penetrating compared to when it doesn't, what the local order is, and now we're studying how that can be changed as we surface functionalize these rods to make them more hydrophobic or more hydrophilic or cross-linked into the Nafion. to try to preserve the ionic conductivity that we have to have through our separation system while still keeping the gas crossover rate low, because if it's ionically conductive but the gases go right through, we might as well poke the hole in the thing. Finally, we're smart, but we know we're not that smart. And so, although it's good that we are studying, like the rest of the community, new systems, it would be even better if we studied more systems in a day than had been discovered in human history. So that's what I challenge the high throughput team to do. I challenge the high throughput team not to make a compound every 5 years, but to make 1 million quantitatively screened and booked every day. They looked at me like I was crazy, but we made 1 million new compounds and quantified their activity last week before lunch. How did we do that? Because now, that's her name, had reverse engineered an inkjet printer to do exactly that. And we now have developed inks for all 20 of the elements that are abundant enough in the earth and could be catalytic, that we want to combine any one of their ratios, and we squirt them out. If you want to measure the light absorption properties of these, it's pretty obvious what you do. You just put them through a dot matrix scanner, and all the stuff that's black we don't want, and all the stuff that's white we don't want. We only want the colored stuff. Right? If you want to do electrocatalysts, we squirt them out onto a display, onto a row column multiplexing display that's just like the one in this display on my laptop, because every pixel is switched by this electronics, and when I switch it on, I can measure the current flowing through it into the liquid, and I can raster right around and measure the activity we seek, exactly those currents, on 1 million pixels on that LCD display in a 30th of a second. So we squirt out these compounds, we cover them with a liquid, and we quantify their activities every 30th of a second for every one of these bar-coded plates. And if you have a large format printer, you can do the math, and it was what I said. If you make 3% gradients of everything, we can make literally 1 million different spots every day and characterize them. We're doing this by inkjet printing, we're doing it by physical deposition, we're doing it by electrochemical deposition. Our goal is, if there is a way that scales to make a compound that matters, we want to make them all because we care that we solve this problem. Right? So if we have to make every possible one, that's fine. But along the way, there were innovations, because if you end up with a spot like this from your inkjet printer, that's really bad news because it's all splotchy. This painting actually sold for $1 million, right? But it's not what we want. And so we had to do bitmap printing to randomize them. We had to develop substrates that could make the contact angle work fine. We had to get uniform thicknesses in gels that we hydrated. We worked it all out in less than 2 years by a team of people, and now we can make these spots. After we make these spots, we have automated UV visible absorption, diffuse reflectance scanners that go across spot by spot for all the stuff that's not white or black and tell you the spectrum, and they book it into a database. We then follow it up with a little hanging meniscus drop, a little set of crawlers that tell us the non-aqueous electrochemistry of every one of those photoactive spots in its voltammetry. We then tell you what the X-ray diffraction patterns are of some of the hits. We're actually collaborating with SSRL to get high throughput X-ray diffraction. Actually, we think we can collect the data really quickly. Solving the powder patterns is another story. Right? So people that know how to quickly solve powder patterns would be helpful, no problem. And then we have high throughput XPS to characterize their surface. So we're using both to be the world's brightest hard X-ray source and what is the world's brightest soft X-ray source in innovative ways. We're developing our own beamlines. We have unlimited, essentially, computer time on NERSC to be able to solve some of these problems. We have access to the team at NSEM to give us atom-by-atom information on the catalyst that we seek, because we and our country really cares about trying to solve this problem, and that's really great. This is our building. It just opened up in JCAP South in May. We moved in, bought some equipment, right next to the ALS, right down the hill in 2 years. This is what JCAP North's going to look like, a $54 million building. We broke ground on it, the CERT building, just a couple weeks ago, and the dedication ceremony is on October the 19th, so you're welcome to all come. We have collaborations with 20 different Energy Frontier Research Centers who give us samples. We give them capability back and forth around the country. We have visitors, people on sabbatical. sharing of materials, sharing of theory and modeling, and we'd love it to have students and postdocs come and work in the hub to learn how to benchmark, to give us unique capabilities and tools, and to help us in our job. So finally, there's a lot of science that these people are doing that I only touched the surface of. We've got new photocathodes. We've got these rapid screening tools. We've got 1 million compounds a day. We've got new anodes. We've got pieces coming online. We've got new beamline capability, and we're just really starting because we don't have the problem solved, but there's a tunnel and there's a light, and we think we have the ability to get from here to there if we all are smart about how we do it. So with that, I hope I've given you some both opportunities and challenges. What my goal was to get at least one of you to say, I've got a good idea on how to help solve one of these problems, and then you need to email me, and then we need to hook up to help make this happen. So if I've done that, it's been a success. Hope that's the case, and thanks very much for having me.
Thank you, Nick. Thank you very much. Any questions for Nate?
When are we done? Everyone always asks me, when are you done?
Maybe let's start with you.
In your tungstens,
Yeah.
in your tungsten selenide system, why this diffusion length decreases with the increase in thickness?
That was the tungsten oxide. That was just an example. It was tungsten oxide, and the diffusion length wasn't actually decreasing with increasing thickness. That was the exponential decay. So that was just a way to probe the diffusion length, because if you take a wedge sample like this, right, when you're exciting the thin part, you collect all the carriers. When you excite the thick part, then you only get them where the photoexcited carriers are within a diffusion length of being collected at the solid-liquid interface. So the wedge just gives you an easy way to probe from the decay of the current with lateral distance what the actual collection length, it's not just the diffusion length, it's the space charge width plus the diffusive part, right, what the collection length is. It's just a way to measure it. So you saw it decay because that was the yield decaying, and then it was being fit to a constant diffusion length.
Okay.
Okay?
And I have another question. You are not using hematite for this as a photo system?
Why? Because two reasons. Well, there's a lot of the scientific community is using hematite, and it's got performance that's marginal at best, only gives you 200 or 300 millivolts of open circuit voltage and a milliamp or two of current. And if you did everything perfectly with that band gap, you might get 6 milliamps per centimeter squared. That's still going to be hugely current limiting for us compared to what the bottom cell's going to have to do. So we don't think it's worth our time and effort to go the extra mile to try to make that work just to get, if we're really, really perfect, 4 or 5 milliamps and maybe 200 or 300 millivolts. So we'd rather demonstrate our pieces with something like tungsten oxide, which is stable in acid, where silicon is, so we can build pieces, knowing that it's not the end either, because it's got a band gap of 2.6 eV, but it already gives us 800 millivolts and more current than iron oxide's ever given anybody. So it's a piece that we can use to demonstrate the system that's here with us now. Iron oxide's not stable in acid, it's only stable in base.
Yeah.
Then we need the photoanode that's stable where the cathode is, right? This is what is a system?
Yeah. Thank you.
Yeah, we wouldn't need to. We actually want to coat it with something like graphene to protect it. So tungsten selenide's band gap's 1.2 EV indirect with a 1.3 EV direct gap right above that. And we're getting 600 millivolts out of that, which is almost at the Shockley diode limit, right? So that's the first crystal we grew, and we did it again, the second crystal. It's kind of like a layered compound, more stable and alkaline media version of silicon, right? So that's really good because it opens up another option for us. Oh, of course. And whether the edges are bad news or catalytic is the real issue. It depends if the edges are bad or catalytic, right? That's why we have to find that out.
Hey, polydice sulfide, that's a great catalyst, obviously, as you pointed out correctly. The petrol industry has been using that for years, as you already pointed out, for hydrogen sulfurization. They invent all kinds of tricks.
You bet.
To decorate the edges with cobalt or not.
You bet.
You asked the question when you were talking about what's the edge doing? Is that a recombination step?
Right.
So,
We're just starting. This community, it turns out, to the best of our knowledge, including me that lived in it, has not taken and translated even the opportunities from that entire body of knowledge of petrochemical and refining catalyst development into the low temperature electrochemical regime. So there is essentially no knowledge of any of how that works under electrochemical conditions at low temperature. There are no papers on it. There's no nothing. So we think this is a great area to go fishing. And it's probably the case, for instance, that, the only electrocatalyst that really converts CO2 into any yield of methanol, you won't be surprised, is copper. Because everybody knows that the commercial CO2 catalyst with hydrogen that makes methanol is copper over zinc oxide. So it makes sense that we should be looking at copper on things like TiO2 as strong support interactions to try to reduce CO2 electrochemically at low temperature. There's essentially zero work on this.
Any other questions? Well, if that's not the case, let's thank Nate again for coming. And we have a poster session.